Well, howdy, physics sleuths and inquisitive souls. Welcome again to Dynamic Gravity. This is going to be a really, really long episode. I know it's horrible. And we are going to lay down some serious forbidden knowledge. I promise you, if you watch this episode from start to finish, you are going to understand neutrinos and gravity better than anyone in the world. Except for, of course, yours truly. Because while I may have taught you everything you know, I didn't teach everything I know. So, it's going to be pretty wild. Um, let's go ahead and get into it, I guess. Start off with the good old drink. Because if you're not doing astrophysics lit, then what are you doing? Seriously, just being a nerd? The difference between nerds and geeks, kids, is nerds are really smart, but they're uncool. They're dorks. They don't get no play. Geeks, they're also really smart, but they are cool. They get play. Basically, they drink and have fun while they do their math, too. All right. So, woo, we are going off into neutrinos. And there's a lot of hopla of people talking about neutrinos like now. Like, oh my God, what are they? They're so mysterious and blah, blah, blah. And it's no wonder why people think this, because, when we go to our ultimate source, Wikipedia, my favorite place of knowledge suppository in the whole world, even though they hate me, um, you know, we look at what they've got for neutrinos. Okay, let's just go over this real quick. Denoted by Greek letter V, a fermion, also a lepton, blah, blah, blah. They interact via the weak force interaction and gravity. But they don't because they're not really pulled by gravity as far as we can tell a whole lot. It's really kind of weird. Neutrino's named because it's electrically neutral. It's really not. But in regards to gravity, it's neutral. I'm going to get you there. Don't worry. We're jumping ahead right now. Things are getting kind of cray cray. The rest mass of neutrino is much smaller than that of any other known particle. This is also not true. I'm going to explain why this is and what's going on here with all this stuff. It's just so much misinformation and disinformation and fake news. It's pretty ridiculous. I mean, they go off like, oh, 3 different types of neutrinos. Okay, that's really good knowledge. That's superb. Okay. um, Neutrinos are created from various radioactive decays. So basically, whenever radioactive decays, when they're emitted, and I'm going to explain why that is. I'm going to explain everything, kids. I'm going to get you there. Come to Papa Bear. Don't worry. I'm going to take care of you. Pauli's proposal, blah, blah, blah. Direct detection, blah, blah, blah. Neutrino flavors, blah, blah, blah. Solar neutrino problem. We're not seeing as many as we thought we would. And oscillations fixes that problem. And blah, blah, blah. It just goes on and on and on. And more about the flavors and the different effects. And, anti-neutrinos. That might be a little interesting. But I guess every particle has an antimatter particle as well. And this is going to blow your mind at the end. The mind blow at the very end is just going to, whoo, don't worry. This is going to be a really important episode for the next hour or 3. However long it's going to take is how long it's going to take. And I don't want to hear no kids in the back crying, are we there yet? No, we're there yet when we go through all the information, you understand it. Nuclear reactions, blah, 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 blah. So you see, speed, neutrinos travel faster than the speed of light somehow, but yet they don't other times. Blah, blah, blah. Don't worry. I'm going to explain all of this. This is all just bullshit. Just blowhards who just repeat other people's ideals that are wrong, and they don't understand them, and they suck, and don't worry. But just to let you know, neutrinos is kind of a crazy subject right now. Nobody knows anything, and all the information is really bad and contradictory. So, let's go into neutrino detectors. Neutrinos are very hard to detect, and I'm going to explain why that is too. So they have these huge vats of like detergent and all sorts of stuff, and hope that a neutrino hits it, interacts with the nucleus or something. Although I hear it can also hit and interact with an electron. Well, maybe that's possible. It'd be very rare. But then again, for it to interact with a nucleus would be very rare too. And I'm going to explain this. But there's a reason why it interacts with the nucleus and not the electrons for the most part. And also, some interactions that we might want to be aware of. Um, let me see here. Yeah, so radiochemical methods. A neutrino is flying by and it will hit an atom of gallium. Okay. And then through beta decay, which basically means it hits a neutron, and in that neutron, it turns into a proton and spits out the electron the neutron was hiding. See, that's the difference between a neutron and a proton, kids, is when a proton gobbles up an electron, it got too close to it for whatever reason, it now becomes a neutron, and that's why its charge is neutral for the most part. But it's really not. But it kind of is. So this is an important clue as to what's going on, all right? So we got gallium 71 turning into germanium 71, okay? We look on the good old periodic table, we can see that germanium is right here, and gallium is right here. So gallium is one proton short of being germanium. But as I said in beta decay, when a neutrino hits a neutron, it interacts with it. I'm going to explain how. And then it spits out an electron. And in that interaction, now you have an extra proton in the gallium atom, which now by definition makes it germanium. That's what's going on there. And essentially, when I can tell, most all neutrino detectors kind of work off this kind of premise. I think there is one I read about that actually works off detection of the actual interaction with the electron. This is unexpected for me, but it is possible. Anything's possible if you have enough conditions in place. But this is definitely not normal behavior for neutrinos, and I'm going to explain why. Okay, and also, it's important in 2015, they gave Nobel Peace Prize to these dudes for basically proving that neutrinos can oscillate, meaning change their flavor, almost their density, periodically as they travel, seemingly just as consequence of their existence. And I don't know, I really haven't had time to delve into the neutrino oscillation issue yet, but it doesn't change anything about how dynamic gravity says neutrinos work. It just is something odd that's going on. But it's very interesting. That's maybe one of my projects I like to go into is to figure out exactly why the neutrinos are oscillating their flavors, okay? And by flavors, this is a very important thing, standard modeled. All this is good. Not so sure about the Higgs boson. I'm just saying the evidence for it was pretty weak. Pretty weak if you actually look at the actual hard evidence, but that's a different episode for a different time. So here's our leptons, all right? These are truly the smallest particles in existence. They are not really just a particle, they are the smallest morsel of energy that can be dispersed, period. And of course, you got the electron, and then in its heavier form, it goes from this mega electron volts, zero point 0.5 to 105, right, from the muon. And then it goes even way higher to 100 or 1,777. This is basically saying that the electron has like more negative charge, kind of. So it's almost like two electrons that have combined, like one electron, and the muon is essentially kind of like two electrons worth of charge that have combined. But they behave as a single electron. And it's very unstable, but it is a thing in the world of physics. It does happen. And fun fact, with muons, if they swap out muons with electrons, they can actually make cold fusion happen. This has been a thing that's been known about for decades. Someone won a Nobel Peace Prize for it. Cold fusion has been a thing forever. But the muons decay so quickly, can only do like maybe 1,000 reactions before it dissipates. And it's not enough to really do much of anything yet, but one day. That's one of my things I want to go into is cold fusion one day. I really love cold fusion. The idea of cold fusion is amazing, but I do have doubts for various reasons. Okay, now we got the neutrinos. Now, a neutrino is essentially just an electron, right? It's an electron, only it's not charged, which means it doesn't have the standard negative charge. It doesn't have a positive charge, but really it kind of does. But I'm going to explain this. Don't worry, we're getting there slowly but surely. And it also has the exact same deal as the electron, being the counterpart to the electron. Yes, the neutrino is the brother and the electron is the sister. They are literally like this, okay? They are the counters to each other. Identical in every way, only exact opposites. I know that seems hard to understand right now, but don't worry, we're going to get there. And so it also has heavier versions of itself where it can have double the charge into one package or triple the charge into, I don't know, maybe quadruple the charge. Who knows with how these things work together with their oscillations and vibrations and everything. But this is something very important to understand. Electrons and neutrinos are identical. They're just opposites. They're brother and sister, just like the electric field and a gravitational field are also brother and sister. They're opposites. And they behave in completely radical different ways because one has dominated space as we know it, like the proton, and the other, the electron, must serve its will. So this is why we don't associate a gravitational field as being the brother force to an electric field, when really it seems pretty obvious, right? When you have two magnets or a magnet working with something, and you're like, wow, it's got its own gravity. It's just pulling up anything that's electrically conductive. Um, yeah, that's because that's exactly how gravity works, bro. The only difference is instead of pulling on just the other parts, it's pulling on the electrons and not just the protons so much. Don't worry, this is all in other episodes. And just to let you guys know, if you're new here, you really need to take time and read my peer-reviewed paper into dynamic gravity. I post it in all the descriptions. It will explain everything to you if you're willing to understand it or try to. Trust me, my math is perfect. I'm the only human on the planet ever. They can perfectly calculate gravity, dark energy, and dark matter with the same equation. Perfect. Zero need for fudge factors. Zero. That's me. I'm the guy. No one else on the planet. Something you might want to think about when you think that I might be bullshit and that other people know what they're talking about. Something you might want to consider. So, this is very important, okay? Neutrinos and electrons, brother and sister in every possible way. Not the same, not same, brother and sister. Okay, now we have to go back. Some of you may recognize this diagram from my last episode I did on photons. All right, you really should watch that episode first because that's a good starting point for where we're about to go. All right, you have to understand what a photon is before you can understand what its counterpart, a poton, is. Yes, that's right. I just threw that out there. I made that up. It is a thing and it is very real. Photons and potons, brother and sister. Photons, potons. I call it a poton because it's similar to a photon, only it's made from the proton. Hence, poton. Proton, poton. Poton and photon. Got it? This is going to be crazy. Don't worry. I'm going to explain everything. So, we have an atom here, right? And this atom is, say, something simplistic like a hydrogen. So we got our proton in the middle, which is really 3 quarks, like 1 up quark and 2 down quarks or whatever it is. And that 1 quark is heavier and it has 8 an electron, and that's why these other quarks want to attract to it. That's what's going on there. And then you got an electron that is... I want it. This could be a problem. Okay. So then we got this electron, right? And it's electric, and these are positively charged, and it goes bloop, and it wants to be around it, because it's attracted, but it doesn't want to touch. Because if it touches, it'll become a neutron, and it still has this repulsive charge of the electron that's in the middle of these guys that's pushing away. So it's being attracted and pushing away, just like dynamic gravity says. That's why I called it dynamic gravity, kids, because it's dynamic interactions everywhere you go. There's no one-way thing. It's always 2 ways fighting each other for equilibrium. Always. Every single time. It's ridiculous. Yin and yang. It's all about. Yin and yang. Yin and yang. So, as it's doing this, a photon will hit it. Bloop. And as it hits it, as we learned before, all a photon is an electron that's been spaced out in time during its creation. So electrons and photons are the exact same thing, okay? So they're just spaced out in time. So they hit it, boop, and as it does it, this is going to make this electron's charge grow, and it's going to pull it closer to the proton. Higher energy state, not higher orbital, higher energy state, closer to the proton. And as it does that, it's going to release an identical photon, essentially in real time as it's swallowing that one, the up and the down, and blah, blah, blah. And that is how photons are released. So basically, any form of heat is going to release photons, okay? It's going to release photons from the electron. And if this same thing happens, because keep in mind, and when you have 2 electric fields together and one of them's moving, now you have the right-hand rule in play. Actually, the right-hand rule doesn't even need to have an additional field, but if it does, then now you have a photon created, or a poton. That's the difference there, guys. It's kind of complicated. So, as the electron moves, it releases photons. Well, guess what? Its brother, the proton, as it moves, it releases potons. It will have its own potons, not photons, potons, reverse photons, that it will release. But it's very, very rare and hard for it to release a higher energy photon. Like if an electron gets moved up really fast by a lot of energy, it will release a high energy photon. So when this tries to release a high energy, guess what? It's really big. It takes a lot of energy to move this, and it has to move in comparison to the electric field it's in to create the photon, which would be the electron. So the electron would have to stay mostly static, at least comparatively speaking, while the proton moves slightly, and then you release a photon. Fun fact, gravity waves, gravitons, whatever you want to call those little morsels of gravities going at the speed of light through the galaxy or universe, those are photons. Those are among the lowest energy photons possible. And I'm going to explain why that is. Okay? So, let us dig deeper. Okay? So, we've already stated that photons are released whenever the proton moves in relation to the electron, which doesn't happen very often because the proton is like 2,000 times larger than the electron. Okay? Basically, if we look at trying to find the right thing and I cannot find it. Yes. If we look at the size comparison or mass comparison, an electron would be like a penny and a proton would be a bowling ball. So this one moves, this one does not, by simple Newtonian laws of momentum and energy. It's going to take a whole lot more energy to move this bad boy than this bad girl right here. Okay? So that's one reason why the only things that really can be released, photons that can be released from nucleuses, are essentially gravitons, which, if you want to look up my older lectures on gravitons or what's going on there, I give you the exact frequency, what dynamic gravity says that it should be for a graviton, the wavelength. And spoiler alert, is essentially the lowest there is that any atom can release. So any matter that is essentially above absolute zero is going to first and foremost be immediately pumping out gravitons, photons, into the universe and whatever direction orientation it's in. Okay, so we've got this guy needs to move if we're going to create a photon. And if we're going to make the highest energy photon, guess what that's going to be? The highest energy that it can be, just like the highest energy that an electron can make, is not a gamma wave. That's the highest photon it can make. But as we learned in previous lectures, especially the last one, the wavelength of a photon, once it reaches the size of an electron, just becomes an electron, and that's it. And that's the highest energy that you can create is electrons, essentially electricity. So it maxes out. It goes bloop, bloop, and then a photon doesn't come out. No. What comes out is another electron. Okay? That's what comes out. So this goes bloop, bloop, and this boy gets spit out at right angle. Bloop, according to right-hand rule. Not the speed of light. It does have the momentum of the speed of light, but the problem is electrons cannot travel the speed of light because whenever they're in a gravitational field, which is the field of the proton, the photons being emitted out, that's going to cause inertial drag forces. And this is what causes time dilation as well. If you want to read my theory and other things, I think I have a whole episode on that bad boy too. Okay, so what happens then, you ask, when we do the maximum amount of movement to move a proton? Bloop, bloop. Does it put out the highest wavelength of a Poton? Bloop. I mean, it's possible. It could if it has the right energy. But if it maxed it out, what it's going to pump out is the highest form of a Poton. And the highest form of a photon is an electron. So the highest form of a Poton is going to be not another proton, because it would have to create 3 quarks, and one of those quarks would have to eat an electron to become like a down quark and then suck up the other quarks. It's just not going to happen. I don't even know if it's possible. It could be. This is one of those questions that really deep theoretical particle physicists should contemplate if they want to accept my math and my theory and everything about dynamic gravity. That's a very good thing that needs to be sorted out, that is beyond me. I'm just not the guy for that. But what it will release is the highest energy signature of an electromagnetic wave, a photon, which will be, guess what? A neutrino. Bloop. And this neutrino is going to be spit out whenever the nucleus of any atom ever moves in relation to the electrons around it. Now, this doesn't happen very often, as I explained, because the mass of the proton is so large compared to the mass of the electron. But there is 2 times that this absolutely does happen, 100%. And this is the origin stories of neutrinos. Is whenever you have nuclear fission, one giant atom breaking apart into 2 smaller ones, or fusion, 2 smaller atoms breaking or combining into one larger one. Any one of those, they're going to have electrons in their shells and equilibrium around them. And while this process is going on, it is going to shift the nucleus very quickly, very fastly, bloop, in relation to the electrons that orbit it or around it, encompass it. So you're going to have probably multiple neutrinos come out of every reaction. I don't know, maybe they've calculated, they claim they've calculated, and I'm not going to challenge their math. I'm not saying everybody's wrong on everything, guys. I'm really not that guy. I'm just saying that they're wrong on a lot of stuff, and I'm the guy to fix it. So that is how neutrinos are made. And in the neutrino page, I mean, it tells you, yes, this is how neutrinos are made, is whenever we have nuclear reactions going on, fission or fusion. Either one is going to release neutrinos. We know this, but nobody on the planet knows why, except for you. You're the man, you're the man, you're the man. So that's why. That's why neutrinos are coming out of those reactions, because they are the antithesis to photons, and the highest form of energy in a photon is an electron, and so this is going to release the highest form of a proton, which is a neutrino. And it's only going to release neutrinos, as far as I can tell, as far as I believe. I might be wrong on this, but I believe this firmly, and you guys should take what I believe seriously. It's only going to release neutrinos if it's in the presence of the counter field. So you got the positive field of the proton, and if it's not in the negative field of the electron, making a complete synergetic electric field, then you're not going to have photons or electrons. My bad, electron. Photons or potons, they're going to be released. You're just going to simply have like a magnetic fields or a gravimetric field. That's a whole episode I made too on gravimetric fields, and we're about to find out how to make one, okay? Beyond what I told you before. We're going to go even deeper down the rabbit hole. All right? So just remember, the proton is very, very heavy and large compared to an electron, okay? This is going to come back. We're going to look at this, okay? And here is a chart from Hubble that just shows you, like once you get into the gamma ray, they get to the size of an atomic nuclei, and then that's it. That's as high as they go. And any higher than that, it just becomes electrons. This is just more proof of this. Radio waves are very long. They can be long, meters, miles, whatever. The amount of gravity waves that we're talking about, though, my man, I mean, they literally, they literally, I think I did an episode on this too. They're longer than the distance between the moon and the Earth. That's how long a gravitational poton is, a graviton, whatever terminology you want to use it on. That's how long a gravity poton is. And who knows what happens if you have photons that release at the frequency of visible light. Who knows? We can't even do it because keep in mind, because the atom is so heavy, the only time it can release anything above gravitational waves is essentially, nuclear fission is going to max it out. But who knows? Who knows what visible light would look like and how it would behave in our world dominated by electron shells and atoms if it were photons, a room full of photons instead of photons. I can't even imagine that, even with all the drugs I've done. I can't even, nothing. I can't form a simulation for it. That's how I figure my stuff out. I just run simulations in my mind over and over and over again, using the parameters I know to be true until finally I find one that works out. And I start going down rabbit holes with it and seeing what it leads. That's the mark of my madness, my genius, my insanity. So, basically, if you, as I said, if you have a flow of electrons that aren't really in a field, a protonic field, you're not really going to have photons being released. I mean, I'm sure it's going to release some, depending on radio waves, whatever. But essentially what you're getting is a magnetic field, all right? A little more complicated than that. We're going to go into magnetic fields in the next episode. So I'm going to break all about magnetic fields and what's going on there. That's going to be a doozy too. But, so guess what? We got electrons. Boop, 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 boop. And we got this electric field, and it's creating a magnetic field. Well, if we could have the brother particle to electrons, the photons, or not electrons, neutrinos. If we could have neutrinos follow a path like this, like we can make electrons do with our conductors and electrochemistry, instead of creating a magnetic field, we would create what I call a gravimetric field. And that would be essentially like a magnetic field, only instead of only working on conductive materials, it would work on everything. It's essentially a gravity field that you're creating. And I can assure you, um, spaceships are definitely going to be creating gravitic fields. Uh, that's just too powerful of a way to create gravity. It would be a gravitic field. The only problem is you have to get neutrinos to follow a path like this. But neutrinos are notorious for just going straight, right through everything, like a light year of lead. Pew! Like it's nothing. Like it wasn't even there. Pew! And everyone's like, oh, it's a ghost particle. It's a particle that died at a Halloween party long ago. And now it haunts physics and it just goes. No, 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 no. Physics is stupid. They don't know what's going on. I'm going to explain what's going on. Okay, but first, I have to explain electric spin. Okay? So, electric spin of an electron. It can have spin up or spin down. Okay? Two different things in every electron shell can accommodate two electrons. Can't have two ups. No. Too much resistance. But if it has one up and one down, for some reason, they counter each other out with their charge by pulling themselves together, but not enough where they touch. I don't know, maybe they form Cooper pairs, and that's could be what's going on. I'm not 100% expert in all that yet. I'll run some simulations. But yeah, that's essentially the dealio. We have electrons can be up and down. Okay, same electron, just in different orientation. And yep, here we go again. Up and down. And it's just they're spinning in different directions. They're both like this. One goes do 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 do, and now they're in the right orientation. And they have to be in this way, or they cannot share. There we go. Hund's rule. They cannot share the same electron shell or energy state unless they are doing this. Okay, if it's just two separates, they're not gonna. They're yeah. So here's what you have to understand. You're asking, why am I telling you about electron spin, bro? You promised to teach me about neutrinos. To understand a neutrino, you must first understand an electron. The reason why an electron can be and spin up or spin down is because of the orientation of the way the electron shells are. They can accommodate both. But with neutrinos only being created from fission or fusion reactions, never from a normal atom state, and because they don't linger in the atom in any way or have any neutrino shell that they can occupy, neutrinos are always going to only have one orientation, okay? And that orientation is going to be, they are always spun opposite linear momentum reference as left-handed, okay? So, neutrinos are always left-handed. Electrons can be left or right. Left or right. Neutrinos always going to be left, because the only way to make them that we know of right now, I'm not saying it's impossible, they can definitely do the same thing as electrons if the right conditions are met. But those conditions are never met in the nuclei of an atom or any atom. They're never met, ever, 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 ever. So, whenever electrons are made, because they can be made from the orientation of an electron and spin up or spin down, they can create a spin up or spin down electron. Boop, boop, boop. They can make both, depending on the orientation of the electron. But neutrinos, always gonna be the same orientation, left-handed. Never, ever, ever gonna be right-handed, because there's no way to have an atom upside down in comparison to itself. You'd have to have two nuclei together and one nuclei, but acting as two. And that just doesn't happen. Okay? Maybe you could argue under fission, maybe once in a blue moon, but it will be a low statistical anomaly. Okay. So, why am I telling you this? I'm about to blow your mind, kids. I'm about to blow it open. You're like, why should I care? This is why you should care. Because I just solved the matter-antimatter symmetry crisis problem. Right here, today, I did that with you as my witness. So, what this is basically saying they believe that in the Big Bang, which there was no Big Bang, it's all bullshit, and that's being disproved now. If you want to know how the universe really began, look up my lecture on the gradual universe. I explain how the universe came to be. But either which theory basically says that matter has to be made, right? And when it's made, you have matter and antimatter being made at the same time. Bloop. Matter, antimatter, right? Matter is left-handed, antimatter is right-handed. Bloop. So, the problem is, though, is that if matter and antimatter are always made together and then annihilate shortly thereafter, where's the gimmick? Where's the catch that makes it so something happens to this right-handed matter and we get left-handed matter left over is the only thing. Sorry, brain damage from the war, kids. Game of death takes a high toll on those who survive. Such is the way. So, basically, that's what this is saying. But they're using some bullshit. Well, we're guessing that about 1 in a billion particles managed to survive with gusto and grit and that can-do attitude. We don't know how, though. This is where they're at. They're retarded. They don't know what's going on. So, that's, CERN's everybody's official take. But it basically saying that, it's a flip coin and blah, 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 which should always be equaled out. Now, the only thing that could sort this problem out is if you had a left-handed particle that loved to interact with quarks because it was essentially of the same energy signature, not the same energy level, but the same energy signature as a quark. And so as you have two quarks being created, one left-handed matter quark and one right-handed antimatter quark, and you have neutrinos just shooting throughout the entire universe, everywhere, in every direction, constantly, forever. Guess what's going to happen? Sooner or later, this pair is going to encounter a neutrino, which is going to interact and neutralize or destroy the right-sided antimatter. And now the left-sided is what remains. So left-handed neutrinos interact with righty quarks, which are made, and all that's left is the left-hand quark. Kind of crazy, right? And why did I throw this in there? Interactions involving right-handed or opposite-handed fermions have not been shown to occur, implying that the universe has a preference for left-handed chirality. implying, yeah, they don't know. Basically, they're just saying, look, we know that the universe is left-handed chirality, which means it's all left-handed. Okay, there ain't no more right. There ain't no right-handed quarks around. All right, it's all left-handed ones. That makes all the matter. And the reason why is because once you get matter made, it starts making neutrinos, which interact with, the antimatter, the right-handed matter, the right-handed chirality, and then what you're left with is all lefties, which describes the universe that we are living in now. Excuse me. So, we just solved the antimatter crisis in cosmology. You're welcome. Where do I collect my check? Do I get a ring, girl? What's my prize? Now, we're going to go even deeper into this rabbit hole, kids. All right? So, we're going to explain the nature of neutrinos, all right? Radio waves can penetrate non-conducting material such as wood and bricks and concrete extremely well. They cannot pass through electrical conductors. This comes into more of my lecture on magnets, which I'm going to give another week or so. I don't know, I might need to do a little more research to make sure I'm on point with that. To be honest, guys, when I do this stuff, I just do a bunch of drugs, run simulations, you just see what pops out. And then I'm like, that sounds good. And then I just like write down quick brief notes, and then I just make this video. That's where I'm at. I know it sounds kind of like shotgun style-ish, but that's how I roll. I'm a cyclone. What do you want? And I explained in my last episodes on photons why like radio waves will penetrate matter much better than, say, like, gamma rays, ultraviolet, visible light, whatever. Well, guess what? You might be saying, okay, Sean, you've got a neutrino that's like an electron, the highest energy state, right? And it's just going pew right at atoms. And it's like the opposite of a photon. But if we had a high energy state photon, that would just get absorbed and dealt with immediately by any atom it comes in contact with. A photon, yes. But I invoke the rule of inverse carnage. And basically what that says, that's a real thing, I just made it up. And basically what that means is if the electron is a negatively charged entity, all right, and the neutrino lacks that negative charge, maybe positively charged, I can't even tell at this point. We'll have to do more simulations. Then, by the design of an atom, where the nucleus is positively charged in the core and the electric negative electron shell encompasses the outside, anything that would interact well with that electron shell, I'm going to say is not going to interact well with that electron shell if it's of inverse qualities or attributes. And ergo the neutrino. So you're like, well, why don't neutrinos interact with electrons? Because electrons interact with electrons pretty well. Neutrinos, being the opposite, do not. But at the counterpart, if we go back to our trusty diagram of wavelength here, if only the higher wavelengths will interact with electron shells on photons, and the lower wavelengths go right through them like they're nothing, guess what? Then photons, and neutrino is the highest form of photon. The higher the photon towards the neutrino, then the less it's going to interact with the electron shell. And the lower the wavelength, like when we have, say, things like gravitational gravitons, whatever you want to call them, gravitational waves, whatever, then those are going to interact more readily. And this works out great for my theory of gravity because it explains why gravity works at all. Because if this were the opposite, it could be 50-50, right? But if it were the opposite way, my whole theory would be in a whole lot of trouble. It'd be like, well, but why would it do that? But if it doesn't, but it does. It does. That's what you need to know. It does. So, gravitational photons interact with electron valence shells very readily. Higher frequency photons and going to extreme neutrinos don't want to interact with electrons at all. And I could not give you a satisfactory answer as to why that is. Like, I can't do it. I honestly don't know the truth. But it is a thing. And now we've explained one part, there's two parts, but one part on why neutrinos pass right through at least the electron valence shells of atoms like it's nothing. But you're saying, well, why doesn't it then interact with the nucleus or just positively charged? It's a good question. Okay, so, we're not there yet. So, basically, where did I do this? Here it is. Good old Newton, right? Momentum is equal to mass times velocity squared. Okay? Mass times velocity squared, or not squared, my bad. That's that's force. Just mass times velocity, right? So the velocity is the speed of light. Pretty damn fast. The fastest anything goes naturally without additional effects. Normally. The momentum is, keep in mind, neutrinos are the brother to electrons. So whatever the mass of an electron, that is the mass of a neutrino. It is. Now, it's going to interact differently because, like I said, the way gravity works is dynamic. That's why I called it that. And so basically, though, if we take the mass of an electron and times it going the speed of light, it's really, really going to have a lot of energy, okay? I mean, we're talking like a ton of energy. How much energy, you're asking? I know. You're like, well, but how much? I want to need proof. Here's how much. This is like Anatoly Bukharovsky, a Russian. He drank too much vodka, so the rumor goes. And he was working in a particle accelerator. And I don't know, he stuck his head in it while it was going. He did that. And it didn't kill him. He survived. But, as you can see, it really messed him up. It just did a beam of destroyed tissue, almost like someone just stabbed him with something that just instantly killed all of his cells. And, there was probably like millions of electrons. But keep in mind, there's like trillions of cells in this pathway, okay? So, one electron, or maybe it's protons, I don't know. It basically did a whole lot of damage. It had a whole lot of energy, okay? It wrecked a lot. A lot. So, when you have something like an electron that has mass, it's going the speed of light. If it hits something, it's not going to budge. It's either going to react and destroy it and create new particles with the energy that it made in that reaction, or it's going to keep on trucking through and literally, bloop, make, let's do this. So here, let's say, is our neutrino, right? Our neutrino is just going, bloop. Let's get these guys out of the way. I'm going to clean path, right? And it's going bloop right through our atom, right here, right? But the neutrino has so much momentum going the speed of light and having mass. And we know they have mass. How do we know they have mass? Because guess what? This Nobel Prize that I taught you about could only happen if neutrinos had mass. It is impossible by all known physics for a neutrino to change flavors and oscillate if it has no mass. Neutrinos must have mass, but they cannot measure the mass because they can't even measure neutrinos barely. They can barely detect when they're there, much less anything about it. So, you got a neutrino going the speed of light with all this momentum. Boop! And it doesn't want to react with the electron. Can't explain why very well that way, but it doesn't. It doesn't want to interact with the electron. It's like, fuck you, electron. Boop! But if it goes across a proton, it will interact with it. And this interaction will occur in one of two things, okay? Either it will perfectly hit the electron that has been neutralized inside a down quark, and either a proton or neutron most likely because it has two down quarks. And hence, now we're right back at our neutrino, thing, where we have it hitting gallium and then undergoing beta decay, where a neutron loses an electron and now turns into a proton. That's right. So the neutrino is going bloop, and it hits the electron and the down quark of the neutrino, the neutron, and turns this into a different atom altogether because it has a different amount of protons now. Okay? That's one way it can interact. But this has to be a direct hit. And it's very rare odds that's going to happen, since neutrinos are realistically what they're actually doing 99.99999% of the time when they go by an atom, they're going bloop. Well, guess what? This neutrino has all this momentum from going so fast, where the atom only has weight from existing. It's not going the speed of light. It's just sitting there. But it is fat. It's a fat atom. But it can't compare to the amount of momentum that the neutrino has. Neutrino, if you calculate, is so much more. So as neutrino goes, we'll slow this down. It comes close to the nucleus, and the nucleus will actually shift the whole atom, because these are actually going to be linked to this. So as this neutrino passes by, boop, 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 it's going to push the proton out of the way from its momentum. And then it keeps going by, boop, boop, boop. And then the proton will find equilibrium again, probably go back to close to where it was before. May even release some sort of higher energy photons that are above graviton level. I would think it would, personally, but I don't know what frequency we're talking about. Probably the equivalents of radio waves at best for photons. You've been talking too long. I need another drink. Hold on. Oh, man. How do I pause this? There is no pause. That's amazing. There is no pause. I'm really sorry, guys. I get a drink. I'll be right back. Okay, oh my god. I know this episode's going on forever. I'm so sorry. This is a huge subject. There's a lot to it. It's monumental. It destroys physics in every way. You have to pay attention the whole way or you suck and you lose all your cool points. I'm sorry. That's the way it has to be. So, sparkling alcoholic water. Ba-bam. Okay. Well, not as alcoholic as the wine, but good enough. So, this is the reason why neutrinos are so difficult to detect. Because as they go through, as they meander through the lives of poor little atoms, the atoms are forced, but to give way and heed to the neutrinos. Bloop. And neutrinos don't want to interact with the electrons at all. They're like, nope. Only if they're in the down quark, or is it the up quark or down? I don't know. I have to look it up again. In the nucleus. And when it somehow gets converted into the strong force, it is what it is. So, you might be asking, well, if that were true, I mean, like if atoms were just constantly bloop, 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 oscillating and vibrating and jiggling constantly from this endless supply of neutrinos going through everything, then wouldn't we be able to detect that and somehow? Yes, you're a genius. God bless you. Here is what happens. Right here. This is always perplexed me. When I created my gradual universe theory to explain how the universe really began and to really stick it to the Big Bang, because screw the Big Bang. They don't know what the hell they're talking about, morons. I could never understood. Because you got, according to dynamic gravity, if you could have an atom that is absolute zero, it will not radiate any gravitational waves. It will not. It may still be affected by gravity. Even that, to be honest, I'm not even sure about. I'm really not even sure, to be honest. That could be one way to make anti-gravity. It gets absolute zero. But anything above absolute zero, now you have heat, right, introduced into the system. And heat is just essentially moving around the jiggling of atoms. That's all heat is, all right? Jiggling of atoms. And when they get close to other atoms, bloop, they hit these ones and they make these ones jiggle and they transfer the heat through conductance. And that's how heat goes. That's all heat is. It's not this magical, mystical energy. It is just atoms dancing. That's it. Atoms moving. That's it. That's all heat is. So, according to this, we know that all atoms in space are not at absolute zero. You think they would be, but they're not. They're at 2.7 degrees Celsius in the deepest part of space, in the voids of space, as far as we can go. The atoms there of hydrogen are still at 2.7 degrees Kelvin, which is just like 2 degrees Celsius above absolute zero. It's just like, it's very, very, very close to absolute zero, but it's not. And that is enough energy for the atoms to move around and hold themselves together and to create the interactions, the virtual particles they need within an atom to maintain the structure, the rigid structure of an atom. It's all done through virtual particles, and that takes energy. And that is why I say gravity itself is derived from heat. Without heat, you cannot have gravity. If you could take the Earth and just magically, poof, freeze it to absolute zero, all of it, every atom, it would have no more gravity. Even though we're not absolute zero, and we could have an insulator say, the Earth would not radiate any gravity and we would just float gently into space into our ultimate demise and doom. Physics can be cold and harsh, my friends. It's not all rainbows, butterflies. So, this now explains why 2.7 degrees Kelvin appears to be the lowest that any atoms will get naturally, even in the deepest, darkest regions of the voids of space. They still have energy coming in the form of neutrinos going, ha ha, bloop, just hitting them and forcing these atoms to move and to create heat enough that they can make physical or virtual particles and create gravity and do what they need to do as particles. Does that make any sense? Now, God, we still got a couple more concepts. This is such a long episode. You can do this. I can do this. You can do this. So, what we need to know, another funny thing about neutrinos is they've been detected as going faster than the speed of light. Okay? Now, they are held because they interact with protons and the positive force and the negative too. They are held to inertial drag forces of virtual photons and potons, which means that they cannot go faster than the speed of light. So you be banging on my faster than the speed of light. They cannot do it. But it has been detected that sources have been sent from various different ways, from supernova and experiments, and they say somehow these neutrinos got there very, very small increment of speed, but they got there just a little bit before the speed of light, before anything else got there. We don't know how. Yeah, because you don't understand what neutrinos are. So, neutrinos are positively charged, or very least not negatively charged. I think positive, they could be neutral. They might not be absent of charge. I don't know. Who knows what's going on when these freaking quarks are wiggling and making these neutrinos. But when a neutrino is made, okay, it has a positive charge, let's say, and this nucleus is also positively charged because it's made of the same thing, the same, like, all right? Even if it's not, even if this charge is not positive and it's negative, who knows? It's still the same. It's like they're going to repel, right? And this this force of same is the force of gravity itself. So, as a neutrino approaches a large celestial object like a planet, I believe, in likelihood, it's going to encounter more force and decelerate. All right? But as it was made from, let's say, a planetary source like a supernova, right? Let's say it's made boop, 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 coming out. Bloop, bloop. You got this neutrino, which is same as this same. It's going to put a force on the neutrino that it would not have on any other particle, where it's going to give it a slight extra boost to make this neutrino go just a little bit faster. All right? And it might even travel through the voids of space, going significantly faster. Maybe even, I don't know, 1% faster. Who knows? Who knows how much faster it's going to, but it will go a little bit faster according to how it was created. But a lot of that is going to come back on the back end when it approaches a planet, and it's going to be resisted by it initially. So, I mean, it's going to be going a lot faster leaving the planet, but as it approaches the planet, it's going to slow down a little bit. So in the end, it should counter out to be about the same speed and the same time, unless, of course, the source that made the neutrino was very large, like a star, and the source receiving the neutrino was not as large, still large, but not as large, and more like a planet, okay? So as the neutrino leaves this star, bloop, 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 it is going to have a whole lot of force pushing it, giving it extra momentum to do its thing. But as it approaches a planet, it only gets a little bit of blowback. Poor planet. And so it goes super fast here and then slows down just a little bit here. And overall, if you count the two together, you get the neutrino is probably, depending on how it's made, probably going to end up traveling just a hair faster than the speed of light. Not much, but a hair. All right. So we've explained this. I hope you caught with me so far, because we're on the final gimmick of this whole thing. All right. The whole reason I tried to master the neutrino is because I wanted to make it create a gravimetric field, like a magnetic field. Okay. But this is really, really hard to do because we don't know of any material that can corral a neutrino because it has so much momentum going in. It has so much momentum as it's traveling and as it interacts with all known matter. You'd have to have some pretty exotic matter that you'd have to create to interact with it, or use a whole lot of force, which you could do. Use a whole lot of force to curve that, but keep in mind, the amount of force that we're talking about is a lot. It's a lot. I mean, now you got to use a whole lot of energy to create gravity, a gravimetric field. But there's one final note I want you to pontificate on as you rest upon the tree of woe. If time dilation is caused by particles being exposed, or things being exposed to more virtual particles, as I contend in my theory of dynamic gravity, you read my peer-reviewed paper, then what would have more time dilation than a neutrino? Than a neutrino traveling at literally as fast as the speed of light, if not faster than the speed of light, under certain criteria. And momentum can be divided up into time, right? You can divide for force momentum by time. So what I'm trying to get at, kids, is it may not be completely hopeless to deal with neutrinos because they are experiencing the most severe time dilation of any known thing in the universe by far. Except maybe a black hole. I always forget about the black holes. Super celestials. But it still might be possible because you do have one thing on your side. Time. Momentum? No, it's not on your side at all. But the time is on your side. So if you can somehow figure out a way to transfer that time dilation into force or lack of force on the neutrino's behalf, then it may be possible to create a gravimetric field as easily as we could, maybe not as easily, but easily-ish, is compared to a magnetic field. And on that note, I wish, if you made it this far with me, thank you. Many thanks. God bless. You are a master of your own mind. And I implore you to look at all my other videos. All of them teach something important in regards to dynamic gravity on this channel, like 50 of them now. And I'm going to have even more coming out. As long as I have something that I feel is worthy of saying in regards to dynamic gravity, I'm going to make a video on it. But this time will not last forever. There'll be a time where I will not make videos anymore, and that will be the end of it, and good riddance. But until then, I bid you farewell. And until next time, I'll see you on Dynamic Gravity.
Like, subscribe, submit.